In this final lesson, we are going to review parametric and polar curves. So first, we're going to review how to graph a parametrized curve. So sketch the curve and indicate the direction in which it's traversed for these specific values of t. So just make a table with a t column, an x column, and a y column, and just fill in the values of x and y for that value of t. So if t is -2, x will be 4 minus 2, or 2, and y would be 5. And if t is -1, x will be -1, and y will be 4. When t is 0, x is -2, and y is 3. When t is 1, the x is -1, and the y is 2. And the t does not get plotted, just the x and y get plotted. So over 2, up 5, back 1, up 4, back 2, up 3, back 1, up 2. And the curve is traced in that direction, so it gives me an arrow telling me what the direction of tracing is. Now next, eliminate the parameter and find a Cartesian equation of the curve. Alright, so we have x is t squared minus 2, and y is 3 minus t. It's probably easiest to solve the second equation for y. Y minus 3 is -t, so t will actually equal 3 minus y. So x will actually equal 3 minus y squared minus 2. And the specific y values that will apply for is if the y is bigger than or equal to, the lowest y value we have is y equals 2, and the highest y value we have is 5. And this is actually also the same thing as -1 times y minus 3 squared minus 2, or y minus 3 squared minus 2. That's also equivalent, so just in case you wrote it that way instead. Now, given the curve x equals 4 sine theta and y is 3 plus cosine theta, let's sketch this and indicate the direction in which it's traversed. Pick a column for theta, theta t, doesn't matter, x and y. So if theta is 0, x is 0, and y is actually 4, because cosine of 0 is 1. Another easy value to plug in is pi halves. At that place, sine is 1, so 4 times 1 is 4. And the y will be 3, because cosine is 0 there. At pi, sine is 0, cosine is -1, so 3 minus 1 is 2. I don't know why I just wrote 3. At 3 pi halves, the x is -4 and the y is 3, and by 2 pi we're back to 0, 4. So 0, 4, 4, 3, 0, 2. So far we've done this kind of thing. -4, 3, and 0, 4 again. There we go. Looks like we have an ellipse, and it's being traced in the clockwise as opposed to counterclockwise direction. Alright, so now the simplest thing to do when you have equations that involve sine and cosine is to use the identity that sine squared theta plus cosine squared theta is equal to 1. Using arc sine and arc cosine is technically not incorrect, but it's not simplified all the way, so you're not going to get full credit for that. Better to say x over 4 is sine of theta, y minus 3 is cosine theta, as opposed to blindly solving for theta. And then noticing that x over 4 squared plus y minus 3 squared has to equal 1. So x squared over 16 plus y minus 3, the quantity squared, equals 1. Otherwise, if you want to say that theta is equal to sine inverse of x over 4, and you want to say y minus 3 equals cosine of sine inverse of x over 4, you have to simplify this first of all, and I also don't think it gets you the entire picture, whereas the one that's box does. So this, bad, don't do it. So given the curves x equals natural log of t and y is 1 plus t squared, find an equation of the tangent line at t equals 1. So the parameterized derivative dy dx is given by dy dt over dx dt. Now dy dt is 2t over 1 over t, which simplifies to 2t squared. So there's the derivative. The slope of the tangent line is 2 times 1 squared, or 2. To find the point, you plug t equals 1 in, not the m. The x will equal natural log of 1, which is 0, and the y will equal 1 plus 1 squared, which is 2. And so our equation, y minus y1 is m, x minus x1, y minus 2 equals 2, x minus 0, or y equals 2x plus 2. So given x equals t plus ln t and y is t minus ln t, find the derivative and simplify the answer, and then find all points where the tangent line is horizontal. So first the derivative, and that should say dy dx, is dy dt over dx dt, and that will be 1 minus 1 over t over 1 plus 1 over t, which is t minus 1 over t plus 1. So the tangent will be horizontal at when t minus 1 is 0, which implies that t is 1. And at that point, the x is 1 plus natural log of 1, and the y is 1 minus natural log of 1. So the point in xy form is 1, 1. Just note to yourself that t has to actually be positive in this case because of the natural logs. So given the same curves, now find the second derivative. So the second derivative is the derivative of the first derivative divided by dx dt. So remember that our first derivative was t minus 1 over t plus 1. So its derivative is t plus 1 times 1 minus t minus 1 times 1 all over t plus 1 squared. And then that divided by dx dt, which is 1 plus 1 over t. So that will be 2 over t plus 1 squared over t plus 1 over t, which is the same thing as 2t over t plus 1 cubed. And this second derivative is 0 at 0 and negative 1, but because t has to be bigger than 0, we actually only consider from 0 on up. If you plug in any positive numbers, the second derivative is going to be positive. So this is concave up on 0 to infinity. And just make a note to yourself that it's not defined for negative t values. So we also had an equation for finding arc length for parameterized curves. So the length of a parameterized curve was given by an integral from a to b, square root of dx dt squared plus dy dt squared. dt. So that'll be an integral from 0 to 1, root. So dx dt is 6t squared. dy dt is 6t squared, squared, dt. Square roots do not distribute. Don't distribute roots. That's bad. You prove that like 7 equals 5. 36t squared plus 36t to the 4th. So no, you may not say root 36t squared plus root 36t to the 4th. That is so wrong. What you can do, though, is factor out the greatest common factor. Left with 1 plus t squared. And notice you can square root that 36t squared. You get 6t times the root of 1 plus t squared. And now you've reduced this to something where you can do a substitution. U can equal 1 plus t squared. du is 2t dt. Change your bounds. If t is 0, u is 1. If t is 1, u is 2. So this is 6 over 2, integral from 1 to 2, u to the 1/2 du. So that's 3 u to the 3/2 times 2/3 from 1 to 2, or 2 times 2 to the 3/2 minus 1. I'm good enough with that. You could also write that as 2 times 2 root 2 minus 1. And we also had a method for finding surface area when parameterized regions were rotated about various axes. So we're going to rotate this region, which I believe is actually part of a circle, about the x-axis. So think back to the formula we had for area of a surface. Rotated about the x-axis was the integral 2 pi y ds, and that ds was the length of the curve, which is like our arc length formula. Here, our integral will go from 0 to pi thirds. 2 pi, you input what y is, which is a sine of theta, and then the ds is the square root of dx d theta squared plus dy d theta squared, just as it was for arc length, and times a d theta on the end. So dx d theta will be negative a sine of theta, that whole thing squared, plus positive a cosine of theta, the whole thing squared. The 2 pi a can come out. And inside that radical, we have a squared times sine squared theta plus cosine squared theta. La-da, that's equal to 1. That a squared roots comes out, multiplies by the other a, giving us 2 pi a squared again. And there we go. Now we're in business. The antiderivative of sine of theta is negative cosine of theta. So 2 pi a squared. Now when you input negative pi thirds into cosine of theta, you get 1/2, so the negative makes that negative 1/2, minus negative 1. So this will be 2 pi a squared times 1/2, which is pi a squared. So that, in a nutshell, is kind of all the stuff we can do with parameterizations. The next thing we discussed was the specific parameterization for polar curves. And in this system, we let x equal r cosine of theta, y equal r sine of theta, where r is usually a function of theta. So in this case, r is not always constant. It can be, but often is not. So first, how do you plot these polar points? So this is your radius, this is your angle. So you start at the pole, and you rotate negative pi 6 degrees, and you go out a distance of 2. And I'll give you a plot to do that on, but that's the basic idea. The conversion formulas are given right here. So if you were to plot this in the Cartesian system, the sort of over and then up or down thing, obviously it's positive x and negative y. Well, x will equal 2 times cosine of negative pi 6, which is 2 times root 3 over 2, or the x is root 3. And the y is 2 times sine of negative pi 6. And sine of negative pi 6 is negative 1/2. So the y value is negative 1. So if you were to plot this point, normally you would go over root 3 and down 1. So that's the Cartesian coordinates for that point. All right, so next let's do the other direction. The Cartesian coordinates of a point are negative 2, positive 2. So let's just plot that. Back 2, up 2. And we want to find 2 sets of polar coordinates for this one point. So the first thing we have to find is the r. And notice that r squared is negative 2 squared plus 2 squared. So r squared is 8. R is square root 8, which is the same thing as 2 root 2. Technically it's plus or minus, so plus or minus those numbers. Now, you can use trig to figure out what that angle is, but you can also just sort of eyeball it. That is pretty obviously a 45-degree angle. You also have the formula that tangent of your angle is equal to y over x. And so that would equal 2 over negative 2, or negative 1. And that will happen, you've got to keep in mind what quadrant that's in. This is, for us, 3 pi over 4. So, all right, so one possible expression of this point with a positive r would be 2 root 2, angle of 3 pi over 4. Now, if we're going to give one with a negative r, so negative 2 root 2, we'd plot that by going to this point and then reflecting. And there are many possible angles that you could give. One would be negative pi quarters. You could have also given 7 pi quarters. So there's lots of right answers for these, but just make sure that you follow directions, and you can show me that you can give one instance where the radius is positive and one instance where the radius is negative. You will also be expected to give Cartesian equations for certain polar curves that are pretty easy to identify by either just thinking about it or using the parameterization formulas. So r equals 5 means you are always 5 away from the pole. Sound familiar? That sounds like a circle. And you can notice that by saying r squared is 25 and r squared is x squared plus y squared. So there's the common equation. It's a circle with r equal 5, center at 0, 0. R equals 4 cosecant theta isn't as obvious until you write it as 4 over sine of theta. Multiply that sine theta over, and you have r sine theta is 4. And r sine theta is y, so this is how you would express a horizontal line in polar coordinates. R is 4 cosecant of theta. So how would you express a line with a slope? Well, y equals negative x. That looks like this. Notice how the distance away that points are varies, but the radius is always anything changing, getting really big or really negative. So this is an angle, and it's a constant angle of 3 pi over 4. You could have also said it's a constant angle of negative pi over 4. That would do the same thing. And this even works when you have negative radii, because if you were to say graph a point with an angle of 3 pi quarters and a negative radius, you would go over 3 pi quarters, flip it down. Back pi quarters, flip it up. So both of those are equations for that line in polar coordinates. Now if we have x squared plus y squared equals 2, this is a circle with r equal root 2, or you could say r squared is 2, which means technically r is positive or negative root 2. Both of those are equations of a circle of radius root 2. So either is okay. Now, when finding derivatives of polar curves, you have to remember that it's not as simple as r prime equals e to the theta. No. You have to remember that you have these parameterizations. X is r cosine of theta, y is r sine of theta. So the best way to remember the derivative, in my opinion, is to remember these formulas and to say, okay, my derivative dy dx, that's dy d theta over dx d theta. And then differentiate the y parameterization. Well, that'll be dr d theta sine theta plus r cosine theta using the product rule over dr d theta cosine theta minus r sine theta. And then input what r is. E to the theta sine theta plus e to the theta cosine theta over e to the theta cosine theta minus e to the theta sine theta. And those e to the thetas can cancel, and we have sine of theta plus cosine of theta over cosine theta minus sine theta. So the tangent will be horizontal if the numerator is 0. Spelling challenged, horizontal. The denominator has to also be non-zero, but this one's not going to get that complicated. If sine theta plus cosine theta is 0, which implies that sine theta is the opposite of cosine theta, and that happens at theta equals 3 pi quarters and also at 7 pi quarters. That's if we're restricting ourselves to 0 to 2 pi. So since I haven't said that, we probably should say theta is 3 pi quarters plus pi n. That accounts for all possibilities. And the tangent to this curve will be vertical if cosine theta minus sine theta equals 0, which means cosine theta equals sine theta, and that happens if theta is pi quarters and 5 pi quarters. Notice how those are also pi apart, so to list them all, you'd say pi quarters plus pi n. So similar sort of idea. Find the slope of the tangent line to r equals cosine 3 theta at theta equals pi over 2. So once again, dy dx, so x is r cosine theta, y is r sine theta, so that will be dr d theta sine theta plus r cosine theta over dr d theta cosine theta minus r sine theta. And dr d theta is negative 3 sine of 3 theta. So we have negative 3 sine 3 theta sine theta plus cosine 3 theta cosine of theta over negative 3 sine of 3 theta cosine theta minus cosine of 3 theta sine theta. Now at theta equals pi over 2, our slope will equal negative 3 times sine of 3 pi over 2, sine of pi over 2, plus cosine 3 pi over 2, cosine pi over 2 over negative 3 sine 3 pi over 2 cosine pi over 2 minus cosine 3 pi over 2 sine pi over 2. So that gives us negative 3 times negative 1 times 1 plus 0 times 0 over negative 3 times negative 1 times 0 minus 0 times 1. And no, you're not mistaken, this is actually 3 over 0. So what that means is that your slope is undefined at that point. You have a vertical tangent. So something of the form x equals some number. In addition to analyzing derivatives of polar curves, you're also going to have to know how to sketch their graphs. This is probably one of the trickiest things, I think, in this unit. So r is 1 plus 2 cosine theta. So I think it's best to start by graphing this in Cartesian coordinates. Here's the theta axis, here's the r axis. First, let's just graph r equals 2 cosine of theta. So 1, 2, 1, 2, 2 pi, pi, half pi, and 3 pi halves. So begin at 2, pi halves were at 0, pi we'd be at negative 2, 3 pi over 2 at 0, and 2 pi we're back at 2. So there's 2 cosine of theta. And then when we add 1 to it, this gets shifted up 1. So that's at 3, this is at 1, this is at negative 1, this points at 1, and that points at 3. And the points where we equal 0, this and this, we solve by saying 0 is 1 plus 2 cosine of theta. Cosine theta is negative a half, and that happens when theta is 7, nope. So that's the x is negative. So this happens at theta equals 2 pi thirds and also at 4 pi thirds. All right, anyhow, first we start at angle of 0, radius of 3. So there's our start point. By pi halves, we're down to 1. We've done this kind of thing. And then once we hit 2 pi thirds, which is this angle, we've gone to 0. And the next part's the trickiest bit. By pi, we're at negative 1, so this point reflects over to here, and all these bitty dots over here, they're going to reflect like this. And then that pattern reverses, so all these bitty dots over here reflect like that. And then by 3 pi halves, we're back to 1, and by the time we get to 2 pi, we're back at 3. So there is the polar curve. Like this, and like that. And now given these two curves, 4 sine of 2 theta and r equals 2, we're going to sketch the curve and then find all the points of intersection. So r equals 2 is nice and easy to graph. Circle of radius 2. We'll see how well you can trace that particular circle of radius 2 that you were given. Okay, and then 4 sine of 2 theta. All right, this will go twice as fast as a regular sine function. So if this is 2 pi, it's gone through 1 cycle by pi. And there's half pi, quarter pi, 3/4 pi. So it begins at 0. By pi quarters, we were up at 4. Pi halves were at 0. 3 pi quarters were at negative 4, and pi were at 0. And then the pattern repeats. 5 pi quarters were at 4. 3 pi halves, we're at 0. 7 pi quarters, we're at -4. There we go. Okay, starts off at the pole. By pi quarters, we're up at 4. By pi halves, we're down to 0. So there's the first loop traced. 3 pi quarters is this angle here. That reflects down to that point. And all these dots here are reflecting down like this. And all these dots here are reflecting down that way. So we've done this and this. Excuse my bad art. By 5 pi quarters, we're at 4 again. So we've done this kind of loop-de-loop. And 7 pi quarters, that's this point reflecting onto this. So loop, 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 loop. And you can see from the picture that we have 1, 2, 3, 4, 5, 6, 7, 8 points of intersection. So one way to find them is to set 4 sine of 2 theta equal to 2, which says sine 2 theta's a half. And this will occur if 2 theta is equal to, well, pi 6, 5 pi 6. You have to account for the fact that you go around the unit circle twice. So plus 2 pi would be 13 pi 6. And then 5 pi 6 plus 12 pi 6 is 17 pi 6. So we get theta is pi over 12, 5 pi over 12, 13 pi over 12, and 17 pi over 12. And you can verify for yourself that all of those numbers are less than 2 pi, so there's nothing repeated in that list. Now the way to find the rest of them for this equation is to notice that r equals -2 is also a circle of radius 2. So we can also solve the equation 4 sine of 2 theta equals -2. And that would give us sine of 2 theta equals -1/2. And that happens when 2 theta is, well, let's think, first one is going to be 7 pi over 6. And then 11 pi over 6. And then plus add 2 pi to both of those. So 19 pi over 6 and 23 pi over 6, which then gives you theta is 7 pi over 12, 11 pi over 12, 19 pi over 12, and 23 pi over 12, and that one barely squeaks in under 2 pi. So let's just point out which ones we found. The first one's in purple. Here's pi 12ths, 5 pi 12ths. So 5 is awfully close to 6, which is awfully close to pi half, so that is this point right here. 13 pi 12ths, so just a little bit past pi, so that must be this one. And 17 pi 12ths is just a hair shy of 3 pi over 2, so it must be that one. So the first equation found us those two. The second equation found us these four. So given the two curves from the previous example, find the area inside the first curve but outside the second curve. So inside the rows but outside of the circle. So let's just, roughly speaking, you have this picture in your paper, but I'll just kind of draw what it is. So you've got a circle and then a petal going like this, and we're looking at finding this area. And the first thing you should notice is there's a whole lot of symmetry there, so we're going to make use of that. So our area will be 4 times the area of the first bit. And recall that the area of a polar region is 1/2 integral a to b r squared d theta. So we'll have the integral from this first intersection point to that second intersection point. Well, that first intersection point was pi 12ths. The second one was 5 pi 12ths. And the outer radius is 4 sine of 2 theta squared. And oh, I shouldn't forget my 1/2 here. D theta minus 1/2 times the integral from pi over 12 to 5 pi over 12 2 squared d theta. And yes, we will combine those. So take out the half, multiply it by 4, you get 2. Integral from pi over 12 to 5 pi over 12. That would be 16 sine squared of 2 theta minus 4. And your best friend are those half-angle identities. So this will be 2 integral pi over 12 to 5 pi over 12, 16 times 1/2, 1 minus cosine of 4 theta minus 4 d theta. Okay, that's 16 times 1/2 is going to be 8. And then if I do that 8 minus the 4, I get 4. So I have 4 minus 8 cosine of 4 theta. Hopefully that's okay. All right, now anti-differentiate. And we're going to get 2 times 4 theta minus, well, that'll be 2 sine of 4 theta from pi over 12 to 5 pi over 12. And now plugging some stuff in, let's just make that 8. So 8 times 5 pi over 12 minus 4 times sine of, well, that will be 20 pi over 12 minus 8 times 4 pi over 12 minus 2 times the sine of 4 pi over 12. And so let's reduce those fractions. That will be 8 over 12 will be 2 over 3. 8 over 12, 2 over 3. So that will be 10 pi thirds minus 4 times sine of, well, 20 over 12. So that's 10 over 6, or 5 over 3, minus, okay, 8 over 12 is still 2/3, minus 8 pi over 3 minus 2 times sine of pi thirds. And at pi thirds, the sine appears to be root 3 over 2. At 5 pi thirds, it appears to be negative root 3 over 2. So 10 pi thirds minus 4 times negative root 3 over 2 minus 8 pi thirds plus 2 times root 3 over 2. All right, so 10 pi thirds minus 8 pi thirds is 2 pi thirds plus 2 root 3 plus root 3, or 2 pi over 3 plus 3 root 3.